In October 2017, astronomers detected a peculiar object entering our solar system from beyond. It defied expectations, slicing past at speeds over 26 kilometers per second, radiating 10 times brighter than any recorded comet, and then accelerating mysteriously, as though propelled by some unseen force. At first, many in NASA dismissed the object, later named Oumuamua, as an odd anomaly. But with new observations, including a more recent detection of an even faster, stranger body carrying never-before-seen chemical fingerprints, the idea once whispered as speculation has begun to solidify. If Oumuamua wasn't alone, the question arises, what other visitors from interstellar space might already be passing through unnoticed? On October 19, 2017, Hawaii's Pan-STARRS Observatory flagged a moving object cutting across the night sky. Astronomer Robert Weryk, reviewing the automated records, noticed its unusual trajectory, something no solar system body could produce. The orbital data didn't resemble any known asteroid, comet, or planetary object. In only a few short hours, calculations reveal values far outside normal ranges. The orbital eccentricity, marked as $1.0, indicated a hyperbolic track, the unmistakable signature of something not bound to the sun's gravity. Analysts at NASA's Jet Propulsion Laboratory reran the data sets, confirming Pan-STARRS' extraordinary find. It was moving too fast for the sun to ever capture it. It was a genuine interstellar traveler, inbound from the depths of space. The announcement electrified the astronomical community. For decades, experts had assumed interstellar objects so rare that no human might ever catch sight of one. Suddenly, official Minor Planet Center bulletins reported the first confirmed evidence. Multiple global observatories, Pan-STARRS in Hawaii, followed by Arizona, Chile, and several in Europe, provided positional updates that tightened the orbital fit. There was no doubt. Its eccentricity of 1.20 sealed its status as unbound, while NASA's JPL released orbital diagrams showing a trajectory punching directly through the solar system. Unlike anything native to it, at perihelion, its speed exceeded 87 kilometers per second, approaching from a steep, unexpected angle rather than the shallow inclinations of familiar comets. Observers quickly realized how close humanity had come to missing it entirely. Oumuamua swung around the sun and was already on its way out before Earth-based telescopes even registered its approach. For Pan-STARRS' team, who normally scan for Earth-crossing threats, stumbling upon an alien visitor from another star was nothing short of staggering. The implications were profound. The solar system was not closed off, but open to the traffic of other stars. A single dataset pushed astronomy forward overnight, sparking the burning question: if this interstellar guest slipped through our surveys, how many others had passed undetected in the vast darkness? The numbers shocked astronomers more than the discovery itself. JPL's orbital analysis revealed something extraordinary. Oumuamua experienced a non-gravitational acceleration, statistically significant at a staggering 30 sigma. This wasn't an error. It was a measurable force inconsistent with pure gravity. Even stranger, the acceleration tapered off with distance from the sun, following an exact inverse square law. Normally, comets speed up from outgassing as they heat, but telescopes worldwide, including space-based ones, found no gas, no dust, no cometary tail. Oumuamua appeared bone dry. NASA's official statements urged restraint, proposing hidden jets or exotic venting invisible to current instruments. Yet, each attempt at explanation weakened as further observations unfolded. Enter Harvard astronomer Avi Loeb, who questioned whether conventional models could explain the phenomenon. In his view, if sunlight alone caused the push, the object must be extraordinarily thin, just millimeters thick, acting like a solar sail. That suggested it might not be a natural rock at all, but perhaps debris from alien technology, drifting either deliberately launched or long abandoned. Publishing in Astrophysical Journal letters, Loeb didn't claim certainty, but argued the evidence supported the possibility, sparking global debate. The reaction was swift. NASA and JPL scientists doubled down on natural theories. Some hypothesized invisible hydrogen outgassing, others exotic nitrogen ice or fragments chipped from frozen worlds similar to Pluto. But each ran into the same problems: how to reconcile the brightness, shape, lack of visible emissions, and unexplained acceleration all at once. None offered a full solution. Oumuamua remained stubbornly unique, leaving astronomy at the crossroads between conventional science and the extraordinary possibility that the first messenger from another star might not simply be a fragment of rock, but something truly beyond precedent. The argument over Oumuamua didn't stay confined to scientific journals. It spilled into global headlines. Avi Loeb defended his ideas in mainstream media and his book Extraterrestrial. By 2021, Loeb launched the Galileo Project at Harvard, a privately financed initiative dedicated to systematically hunting for signs of alien technology, whether interstellar objects like Oumuamua, unidentified aerial phenomena within Earth's skies, or technological debris resting on the seafloor. The project's guiding principle was direct: gather new data, avoid speculation unsupported by evidence, and treat every unexplained detail as a potential piece of the puzzle. Using purpose-built telescopes enhanced with artificial intelligence to scan the skies, the Galileo project set out to ensure the next interstellar visitor would be tracked before escaping observation, and that even the strangest hypotheses would be evaluated against hard data. This debate wasn't just about a single object. It was a clash of paradigms, one school insisting the cosmos was strange but wholly natural, the other urging that the possibility of extraterrestrial technology should not be dismissed. For Loeb, the extraordinary 30 sigma acceleration reported in Oumuamua's trajectory was more than a quirk. At the razor edge of measurement accuracy, it looked like the universe offering a message through unexplained messengers. NASA, on its end, grasped the challenge. If old models failed to explain these anomalies, new frameworks would be required. For the Galileo project, the objective was even sharper: never turn away from anomalies, because the next one might not just stretch current models, it could force a complete rewrite of the rules. On July 1st, 2025, the Atlas Survey Telescope in Chile flagged another interstellar candidate blazing through the outer solar system at nearly 58 kilometers per second, far outside the capture range of Jupiter's gravity. Hours later, the automated processing chain issued a minor planet center alert. The orbit was unmistakably hyperbolic, eccentricity over 6.2, with a trajectory pointed out of the Milky Way's thick disk. Within a day of its discovery, NASA's Planetary Defense Coordination Office confirmed it publicly. The third interstellar visitor had entered the solar system. Unlike the scrambles surrounding Oumuamua, this time astronomers were ready. Atlas, under Larry Deno and John Tonry, had built its detection network precisely to catch such high-speed intruders. Telescopes stationed in Hawaii, Chile, and South Africa streamed observations in real time to the MPC, where anything with eccentricity above 1.0 was flagged. Atlas had netted an inbound traveler moving so fast the sun's gravity barely touched its course. By that very night, observatories from Arizona to La Palma joined the effort. The Canada-France-Hawaii telescope assembled deep exposures, confirming a faint haze of activity consistent with early predictions. Meanwhile, the Zwicky Transient Facility at Palomar scanned its records and uncovered pre-discovery frames going back to June. Each added measurement refined the orbital path. The solution painted a dramatic picture, incoming at 58 kilometers per second on a retrograde orbit tilted nearly 175 degrees to the ecliptic, set to cut through the inner solar system before 4 months passed. NASA's improved alert network, perfected since the near miss with Oumuamua, sent an immediate notification to the planetary defense community worldwide. Before dawn in California, JPL's orbital analysts had already published a trajectory diagram, showing the object would dive inside Mars' orbit by October. The MPC's electronic circulars stamped it officially with the Discovery designation 3I/Atlas. For the first time, astronomers had intercepted an interstellar object on approach instead of after its departure. The detection pipelines, Atlas nightly sweeps, MPC's real-time analysis, and NASA's rapid alerts had worked seamlessly. This time, humanity wouldn't lose its chance, and what it revealed broke expectations yet again. The James Webb Space Telescope's first infrared spectrum of 3I/Atlas challenged every prior benchmark. Instead of mostly water vapor, JWST registered overwhelming carbon dioxide emissions. The numbers were startling: 129 kilograms of CO2 released every second from a nucleus, while water trailed at just 6.6 kilograms, an 8-to-1 ratio. Utterly unlike any solar system comet. Statistically, the result was solid, standing 6 sigmas above the distribution for known comets. This wasn't an observational glitch. It was a distinctive chemical fingerprint, alien to anything local. JWST's instruments revealed even more: carbon dioxide streaming in a broad arc toward the sun, while tiny water ice grains under 1 micron rode the flow thousands of kilometers outward before sublimating. The ice seemed amorphous, a mark of extreme cold formation in ages past. Even the isotopic signatures etched into the carbon told a story unfamiliar to earthly astronomers. The spectral fingerprint of carbon, 13 within the carbon. Dioxide from 3I/Atlas aligns well with average galactic values, yet its overwhelming dominance of CO2 indicates an origin zone far removed from the familiar chemistry of our solar system. Ground-based follow-ups added even more intrigue, using ultra-precise instruments. The European Southern Observatory's Very Large Telescope recorded an unexpected signature, a persistent outflow of atomic nickel vapor without the usual presence of iron, across more than a month of observations. As 3I/Atlas move inward from $4.45 to $2.85, the nickel release increased steadily, climbing from roughly 1 gram per second to close to 5 grams per second. For comet science, that wasn't just noteworthy, it was unprecedented. This marked the first detection of nickel emission ahead of cyanide and in complete isolation from iron. In every known solar system comet, nickel and iron appear in lockstep, reflecting the average cosmic mix. But here, nickel appeared solo. The prevailing theory suggests some unusual nickel, carbon-bearing compound, forged under exotic carbon-rich conditions, is fragmenting under solar heat, liberating nickel atoms while the iron remains trapped within the dust. Such a chemical footprint doesn't resemble anything observed in Oort cloud or Kuiper belt comets. Taken together, the CO2 dominance, the absence of iron, and the isolated nickel vapor, it signals an origin well beyond the CO2 ice line. Perhaps it formed in a protoplanetary disk exposed to harsh stellar radiation or deeper in the dense stellar population of the Milky Way's thick disk. To some astrobiologists, the implications go even further. Exotic molecules may ride on these interstellar bodies as carriers of prebiotic chemistry, potentially seeding life or scattering chemical information across the galaxy for eons. Members of the VLT spectroscopy team have even begun to contemplate whether organometallic pathways, nearly absent in local comets, might be routine in older, metal-poor cosmic environments. Every new ratio, every elemental line, reframes the question of how diverse the galaxy's recipe for building comets, and possibly planets, really is. If 3I/Atlas delivers such radical chemistry, it forces the larger question: what else could be hidden among the endless flow of interstellar passers-by? Its strange molecular fingerprint cannot be swept aside. It demands comet formation theories evolve beyond the comfortable confines of local physics. This makes the path forward clear. If one interstellar visitor can carry such a strikingly alien profile, maybe the anomaly isn't rare at all. It might represent the new normal. A turning point in survey astronomy is arriving. The Vera C. Rubin Observatory, equipped with its 8.4-meter mirror and monumental 3.2 gigapixel camera, will scan the southern skies with high cadence, imaging the entire sky every few nights. Its Legacy Survey of Space and Time, LSST, is designed to catch precisely such phenomena: fast interlopers, faint drifters, and outliers that fail to obey the solar system's usual orbital patterns. By photographing each piece of sky hundreds of times across a decade, LSST will build a dynamic time-lapse of solar system traffic, exposing motion and outliers against the cosmic background. Early projections suggested this survey might uncover 1 or 2 interstellar visitors per year, but new simulations, applied to real LSST field data using advanced in-field tracking algorithms, have shifted those expectations dramatically. Some groups now argue Rubin could detect as many as 70 interstellar objects annually, depending on their true galactic population density. Even the most reserved forecasts, like those from Hoover et al. 2022, place the count at a minimum of 15 such objects within LSSD's first decade. These aren't arbitrary figures. They are grounded in population synthesis, incorporating the discovery conditions of Oumuamua and 2I/Borisov, and now 3I/Atlas, to strengthen their models. Michelle Bannister, a leading astronomer in the field, wagers around 21 detections, while projections from the SETI Institute envision a complete transformation, moving from isolated case studies to full statistical catalogs of interstellar populations. Yet capturing this incoming flood of data exceeds human capacity. Each night, Rubin systems will generate millions of moving light points, each with unique trajectories and brightness variations. Identifying interstellar candidates is not something manual scanning can accomplish. Machine learning, therefore, will carry the load. Researchers are training decision tree ensembles like random forests and gradient-boosted classifiers, fed large batches of simulated LSSD data to recognize anomalies in motion consistent with unbound visitors. The power lies not simply in velocity, but in the orbital arc. Unlike bound bodies, interstellar objects slice through the solar system in singular, unrepeated paths. Numerical digest scores, which encode these orbital peculiarities, have proven even more reliable than raw positional or brightness data. Tests show these AI approaches already approaching near-perfect recall and precision, flagging candidates quickly enough for follow-up before they slip back into hidden trajectories. At the bleeding edge, experimental teams are probing quantum-assisted algorithms as an accelerator. With quantum parallelism, entire LSSD data streams could theoretically be sifted continuously in real time, identifying subtle correlations that might evade classical computation. Some pilot studies with quantum support vector machines have already demonstrated success on synthetic astronomical datasets, classifying high-dimensional parameters and isolating rare outliers resembling interstellar bodies. While quantum AI remains largely experimental, these early tests hint at a future where the detection of interstellar guests becomes routine, and the galaxy's messengers are cataloged and studied rather than lost to the void. The effort is still in its infancy, but the foundation has been laid: new hardware, advanced algorithms, and the determination to exceed today's limits. The implications are profound. If the Rubin Observatory's forecasts are accurate, astronomy may soon shift from interpreting isolated enigmas to charting the entire traffic of interstellar bodies crossing our solar system. That means more than spotting the next Oumuamua or 3I/Atlas. It means building a statistical atlas of their origins, trajectories, and chemical compositions. For the first time, the data won't just describe what passes through. It could forecast what's headed our way. Every new interstellar object that streaks across the night sky brings with it a challenge: to rethink humanity's place within a galactic ecosystem. The outdated vision of the solar system as an enclosed, untouched domain no longer holds. With each confirmed arrival, the line separating out there and right here grows indistinct. Current models suggest that dozens of interstellar travelers may cut through our region every year, each a survivor carrying chemical traces from the chaotic youth of another star. If even a portion of these objects harbor complex molecules or the raw ingredients of life, the prospects of biological exchange between star systems increase profoundly. Recent research in Nature and Astrobiology exploring panspermia indicates that the spread of organic matter across stellar distances is not only possible, but might be a predictable outcome over billions of years. By 2025, Harvard's Galileo project had already begun designing mission protocols aimed at rapid interception and sample return, strategies meant to capture these fleeting visitors before they vanish forever. The reasoning is straightforward, with the ability to analyze, or even return, material from an interstellar body. Humanity would move from being observers of cosmic traffic to active participants. The consequences extend far beyond curiosity. Each interception is an opportunity to test whether life is a cosmic accident localized to Earth or shared inheritance seeded across systems. If even a sliver of an interstellar comet were discovered to contain amino acids or compounds stranger still, it would force a rethinking of biology itself, as well as models of how worlds and planetary systems form. NASA's Project Lyra and the European Space Agency's Comet Interceptor are already charting mission concepts capable of rendezvousing with hyperfast objects, using solar sails or gravitational assists to catch them. In terms of technology, the possibility is already within reach, but the opportunities are fleeting. Capturing an interstellar body is more than a scientific coup. It is a chance to literally touch the deep time of the galaxy, holding direct evidence that planetary systems are interconnected by more than empty space. For explorers of the future, the mission is clear: transform these passing cosmic encounters into discoveries. For the rest of us, the lesson is equally powerful. The solar system is open to visitors, and isolation is no longer the story. On October 19th, 2017, Pan-STARRS caught sight of Oumuamua, racing at 26.55 kilometers per second on a hyperbolic path, accelerating for reasons no one could fully explain. That single detection reverberated through science. Then, in July 2025, 3I/Atlas appeared, moving at nearly 58 kilometers per second and presenting a chemical signature unlike any comet in the record, a staggering 8:1 carbon dioxide to water ratio, laced with nickel vapor absent of iron. Within days, NASA, the James Webb Space Telescope, and the Very Large Telescope confirmed the findings. The pattern was undeniable: 2 distinct interstellar objects within a decade. The trend forced planetary defense offices and space agencies to update expectations. According to Rubin observatory projections now being published, dozens more of these wanderers may be detected annually. Yet the ultimate questions linger. Where do they come from? And what exactly are they? Some point to the Galileo project and advances from ESA as signs that the real search has only just started. What can no longer be disputed is that our solar system is not insulated from the galaxy around it. The data shows clearly the interstellar visitors will keep arriving, whether they are natural relics or fragments of alien engineering. They are redefining what it truly means to inhabit a connected cosmos.